Hi, my name is Wyatt Barnes, and this is another video essay, number 3 for the first exam for Bio 461. Today I'll be talking about the autonomic nervous system, or the ANS, and its two divisions, which are the parasympathetic nervous system and the sympathetic nervous system. And then we'll be talking about a third system within our nervous system, which is the somatic nervous system. Alright, let's get right to it. So first of all, we have the autonomic nervous system, or easily referred to as the ANS. And with it, we have our two subdivisions. We have the SNS, sympathetic nervous system, and the PNS, parasympathetic nervous system. Now, there are a lot of similarities between these two systems, and there's also a lot of differences. So let's go over what's similar between the two, and then we can go on to what's unique between the two. Both of these have what is known as a two-neuron pathway, meaning they have their first neuron stemming from the central nervous system, which is the brain and the spinal cord. I'm drawing a little brain and spinal cord for a visual effect here. Some squiggly lines on the brain. So we have our first neuron that has the cell body inside the central nervous system and extends to what is known as a ganglion. It's kind of a funny word, ganglion. But basically, for our purposes, ganglions are just bundles of nervous tissue where we have synapsing, or transferring of message. And then, so that's the first neuron for each. And then we have a second neuron extending from some ganglion, like as so, onto a part of the body that it transmits a message. Same thing with our sympathetic nervous system. So both systems have this two-neuronic pathway. We have a neuron beginning within the central nervous system, branches out, synapses, or transfers a message to a ganglia, or bundle of nervous tissue, which further synapses with what is known as a post-ganglionic neuron. This is a very common pathway that is super important for controlling things such as our heart rate, blood pressure, our pupil dilation, our vessel constriction, and a number of other things. Let's get into some of the differences between our sympathetic versus parasympathetic nervous system. So, one really easy difference to note between the two systems of sympathetic versus parasympathetic nervous system is that sympathetic nervous systems will have short preganglionic. So I'll put short preganglionic neurons. So that first neuron that we began in the central nervous system is going to be much shorter than the one that will be after we have a synapse with that ganglion, or our post-ganglionic neuron will be much longer than our preganglionic neuron. So I'll just put short pre here and long post. Now you may have already guessed this, but our parasympathetic nervous system is going to be just the opposite of what we just said for our sympathetic nervous system. So our parasympathetic nervous system is going to have very long preganglionic neurons and very short postganglionic neurons. Now, something that's really important to know is in both parasympathetic as well as sympathetic nervous systems, in our preganglionic neurons, they have this special feature where they have something called myelin surrounding or bundling the neuron. So I'm going to draw myelin in blue here so we can see it well. Notice how I put only the blue parts on the pre-ganglionic neurons and left the post-ganglionic neurons bare. This is a great representation of how both the sympathetic and parasympathetic nervous system have myelinated pre-ganglionic neurons, but naked post-ganglionic neurons. And the reason why that is myelin helps improve how quickly we're able to send messages. So when we get a stimulus in the brain that says something needs to change and we are trying to send a message down to some part of our body, that myelin oftentimes will help make that message go really fast. Now, our post-ganglionic neurons are not myelinated, so they don't have the same efficiency, the same amount of efficiency or quickness in transmitting a message. And we'll probably get to that in a bit of why that might be. But for now, we'll move on. So let's talk about the origins of the sympathetic and parasympathetic nervous systems. Starting with the sympathetic, so the SNS. The SNS, as we said before, begins inside the central nervous system, within our spinal cord to be exact. Our spinal cord is kind of divided oftentimes by anatomy into a couple different sections. We have what is known as our cervical section, which in non-medical terms is just known more commonly as our neck. And then we have our thoracic section, which in most people's vocabulary just means your chest. Then we have our abdominal or sacral region, really lower. Sacral is more pelvis, but abdominal sometimes is referred to as sacral, depending on how low we're talking. I'll go ahead and add in sacral here on the very bottom as well. Sacral is kind of like where our pelvis is. So those are the divisions of the spinal cord. The sympathetic nervous system has its nerves, or its preganglionic neurons, or bundle of neurons, coming from T1, which is the first thoracic opening for nerves, all the way down to L2, which is the second branching from the lumbar region, which is kind of down in between, somewhere between abdominal and sacral. All of the spinal cords that branch out here will have sympathetic nervous system neurons. Those neurons will extend, most of them, to what is known as sympathetic chain ganglia. Remember, ganglia meaning just a bundle of nervous tissue where we have a transmission of message, and that bundle of tissue is going to be on the same kind of uniform either side. I drew them as dots here, parallel to our spinal cord. And that is kind of the location, or the anatomy, the basic anatomy of our sympathetic nervous system. Now let's move on to our parasympathetic nervous system anatomy. So parasympathetic, PNS. I'll draw out our central nervous system here again. We have our brain and spinal cord. I apologize for the bad drawings. Hopefully you can follow along still. So, our parasympathetic nervous system extends from what is known as our, goes from the brain, basically, all the way down to the sacral region, or that pelvis region I was talking about before. So that's usually anywhere between S2 to S4. So parasympathetic nervous system kind of takes the cake. It is coming from almost the entire central nervous system with that pre-ganglionic neuron. Now, there is a very important nerve named as the vagus nerve that goes from here and goes kind of into or through our collarbone and goes all the way down through our thoracic and abdominal cavities and down into our sacral region. And the vagus nerve is responsible for approximately 75 to 85% of all parasympathetic nervous system neurons. And that's why we're able to get a lot of organs are innervated through the or all organs are innervated through the parasympathetic nervous system. But that's kind of like the main highway, if you will, of how they get there. And those are the basics of the parasympathetic and sympathetic nervous system and their origins. Let's talk about neurotransmitters. For the parasympathetic nervous system, neurotransmitters is a pretty easy topic. We have our preganglionic neuron represented here with the cell body here and the synapsing end here. And then we have our ganglia. And then we have our postganglionic neuron. And when a message is sent through here in our parasympathetic preganglionic neuron, it synapses or sends a message with neurotransmitters. Now, the specific neurotransmitter here is always going to be acetylcholine, or it's very commonly abbreviated as ACH. When we go here and synapse with our postganglionic neuron, we are going to use the same exact neurotransmitter, acetylcholine, ACH. So when it comes to parasympathetic nervous system, it's pretty easy. You just know that it's going to be acetylcholine both times. So there's two possible points of having a neurotransmitter, and that's both taken by acetylcholine in the P and S. Now in the SNS, we have still acetylcholine in this first synapse, but then in our postganglionic neuron, in our sympathetic nervous system, it's going to be something else. And it's often something such as what is known as NE, or neuroepinephrine. Sometimes it's also just epinephrine, which is another word for adrenaline. But it's usually NE. And sometimes it's just E. So sympathetic nervous system is a little bit more complicated to memorize because there is that difference. But that first synapse on both the P and S as well as the S and S is going to be that acetylcholine, or ACH. Now in both the PNS as well as the SNS, there are three possible destinations of where they can innervate. They can innervate, and I better write this down because this is a key concept to understand. They can innervate smooth muscle, they can also innervate cardiac muscle, finally, they can innervate glands. Now, this is important because most of our organs, our internal vital organs, are smooth muscle. And we have one source of cardiac muscle, and that's our heart. So when we're talking about smooth muscle that affects things such as our blood vessels, we could be talking also about our intestines, we could be talking about our stomach, we could be talking about our liver, we could be talking about our spleen. All of that would be considered smooth muscle and is controlled by both the parasympathetic and sympathetic nervous system. They monitor those organs and they can either slow them down or turn them up so that they're working harder. Same thing goes for our cardiac muscle, aka our heart. We can either slow it down or speed it up, depending on the situation and the stimulation that we're sending from our brain, or not even from our brain, from the central nervous system, spinal cord, or the parasympathetic sympathetic nervous system. We can control this thing without needing to think about it, which is nice. And then finally, glands such as our adrenal glands, which come from the adrenal medulla, which sits right on top of our kidneys, which releases adrenaline. As you might guess, the adrenaline stimulation or release of the adrenaline primarily comes from our SNS, which is our sympathetic nervous system, also known as our fight or flight. So those are the three things that we can innervate with our PNS and SNS. There is nothing else. We will never be innervating skeletal muscle with either of those two systems. But speaking of skeletal muscle, let's talk about what does innervate skeletal muscle. We have two main systems that innervate skeletal muscle, known as somatic nervous system, as well as sensory nervous system. We won't be talking about sensory nervous system today. I'll let you guys sit on that intrigue until next week when I post a video about that. But this week we will be talking about somatic nervous system. Somatic just means movement, physical movement, somatic nervous system. I'm not going to call it SNS because we already have an SNS, but somatic NS nervous system. Somatic nervous system is basically the system that controls our movement. So when I move my arm like this, that's my brain sending a message down through my somatic nervous system into my bicep telling me to lift my arm like that. Now, the really big difference between this and the two other systems we've been talking about is this is voluntary, meaning we have to think it in order to do it. We get to control how we move, which is pretty nice. Sometimes there are some genetic disorders where people are not able to control how well they move, and that can cause some difficulties and complications. Now, the origin of a somatic neuron, speaking of which, beforehand, with the parasympathetic and sympathetic nervous system, we had the two neuronic system, right? The preganglionic neuron that started in the central nervous system, and the postganglionic neuron that started in the ganglia, basically, outside of the central nervous system. In the somatic nervous system, we only have one single neuron. And now remember, the difference between a neuron and a nerve is that a nerve is simply put a bundle of neurons, so a lot of neurons stuck together that go to a similar place. But instead of drawing a brain this time, let's pretend like this is a cross-section view of our spinal cord. Inside of your spinal cord, you'll see something that looks a little bit like this. The middle section will be a little bit more gray, and the outer section, like out here, will be a bit more lighter colored. We call this gray matter, and we call this white matter. And the gray matter is where all of the cell bodies are kind of congregated, where they come together. This is where our somatic neuron cell body lies. This is also where the preganglionic PNS or SNS neuron lies, where their cell bodies lie. It's like a bunch of cell bodies. That's what makes it a darker color. That's what makes it gray. But the difference between the somatic neuron and the PNS or SNS neuron is that the somatic neuron comes out through what is known as the ventral horn of the spinal cord. Ventral is a word that just basically means the front or the belly. So it's going to come out of one of these two front horns, like so. And it will follow the nervous tissue, the spinal nerve, all the way out to some sort of skeletal muscle. This could be your bicep, could be your tricep, it could be your glutes, it could be your calf, some muscle. It doesn't matter which one. Just choose your favorite. And once it gets a message all the way down there, the neurotransmitter that we use here, if you want to pause the video and guess, you're free to do so. But it's acetylcholine again, our friend ACH. So this is really nice because it makes it easy for us to memorize. Because remember, the PNS has the two options for synapsing, so it has two neurotransmitters, but really it's just one, right? Because the preganglionic transmits acetylcholine, the postganglionic also transmits acetylcholine. The sympathetic nervous system is the only weird one where you have to memorize something a little different. The preganglionic neuron is still just acetylcholine, but then the postganglionic neuron is going to be something different. Usually it's norepinephrine, which is represented with just Ne, or it could be just epinephrine. So it kind of depends on where you're going, but that's the essence of it. So we've kind of talked about the general pathway of these three systems. Now we're going to talk about the receptors, or how they affect the parts of the body that these systems go to. So the PNS is parasympathetic nervous system, is also known as the rest and digest system. The SNS, or the sympathetic nervous system, is known as the fight or flight nervous system. And then the somatic nervous system is just movement, which is another way of saying contraction and relaxation of skeletal muscle. On the end of the parasympathetic and sympathetic nervous system, we have three possible things. We have either smooth muscle, aka organs, cardiac muscle, aka your heart, or number three is glands, such as sweat glands, or the glands in your adrenal medulla to release adrenaline into your system. So there's going to be receptors on all of these. So inside of your organs, or on top of your organs, on the surface of them, we have cells with receptors. And different kinds of receptors are binding to different kinds of neurotransmitters and have a different effect on said organ. So say we have an organ. Say we have a cardiac cell. So on our heart we have a cell. And this is the cell. Let's just pretend it's on the heart, and the whole whiteboard is the heart. And on the cell of our heart, we have two receptors, two types of receptors. There's a lot of them, but just two types. We have a receptor known as M2. And then we have another receptor known as beta 1. We'll get into what those mean actually right now, because that's what we're going to do. But the M2 receptor is also known as the muscarinic receptor. Now, a muscarinic receptor is essentially a receptor of the parasympathetic nervous system, or a parasympathetic neuron in this case. So when we have our M2 receptor, which receives acetylcholine, because remember, acetylcholine is both presynaptic and, preganglia and postganglia in our PNS. When it receives acetylcholine, it goes through a process and stimulates, or it actually slows down the heart. So we have a decreased heart rate when we have an increased M2 stimulation. So if we have a lot of stimulation from our parasympathetic nervous system, we have a lot of M2s binding to acetylcholines, which in turn creates a slow heart rate. So we have a very low heart rate when we have a lot of these activated all at once. Now, you might have already guessed, but the beta 1 receptor is something for our sympathetic nervous system. Sympathetic nervous system is fight or flight. So you might guess that if the effect that this receptor would have is increasing our heart rate. Now, the beta 1 receptor is a part of a family of receptors known as adrenal receptors, or adrenergic. I can write it down for you because it's hard to say out loud. Adrenergic. That word. Adrenergic receptor, meaning receptor of adrenaline, or in this case, receptor of norepinephrine. Remember, another word for adrenaline is epinephrine. Norepinephrine is a very similar compound that has a lot of the times a very similar effect. So when we have from our postganglionic neuron of our sympathetic nervous system, when it releases norepinephrine, NE, it will bind to this receptor, our beta 1 receptor on our heart, and it stimulates an increase of heart rate. The contractions will go harder and they'll go faster, so we'll have an increase of heart rate. We can apply this system to other organs, such as our eyes. Every single organ in our body has this dual innervation system, where we have some neurons innervating from our parasympathetic and some neurons from our sympathetic systems. So say we have an eye. That's the pupil. Now the smooth muscle, in this case, there's two muscles within our irises, right? There's the actual iris muscles. That's what the lines are. And then the circle itself is a sphincter of a separate smooth muscle. Now in our eyes we have two receptors, one from the PNS, one from the SNS. The PNS receptor is M3. Now what M3 does is it's found on the smooth muscle of the sphincter, and it actually will excite that sphincter quite a lot. And so if we have a high stimulation of M3, remember, all parasympathetic is going to be using the neurotransmitter acetylcholine. So when we have acetylcholine stimulating this receptor, it actually is going to restrict or constrict our pupils, make them smaller. And so if we have an overstimulation of our parasympathetic nervous system, one symptom that we can see is our pupils won't dilate very well. They'll stay constricted. We'll have really small holes. Yeah, that's what those are called. Anyways, the SNS receptor for eyes is going to be alpha 1. And that will be controlling the iris muscles themselves, these lines here. And the chemical or the neurotransmitter that will be binding to alpha 1 is going to be norepinephrine. We can go on and on. We can do the same example with similar receptors from both systems to any other organ in the body. But the gist is we have this dual system where we have one system controlling to make our organ do one thing, whether it's like to slow down, and then another system to make it speed up. And since we have both, we're able to get some pretty good control over how our body works, which is good. Now for motor control, it's all going to be acetylcholine because it's just one synapse that happens because it's only a single neuron instead of the two neuron system that we see within our PNS and SNS. And so acetylcholine will bind to our receptors, or nicotinic receptors. Those nicotinic receptors are in the what's called as the neuromuscular junction, which is a really fancy way of saying where the neuron kind of like not touches but comes to the muscle. And they're called nicotinic receptors because they were discovered when scientists like put nicotine on a cell, and they observed that it got excited because nicotine also binds to those receptors. But acetylcholine does the same thing, and when that happens, it causes an action potential within the cell, which releases calcium into the cytoplasm or sarcoplasm, which is the space inside of a muscle fiber, which excites all of the fibers within, and we have contraction. Essentially, that is what the somatic nervous system does. Thank you for watching my video. Hope you enjoyed it, and I'll see you next week, probably talking about the sensory nervous system. Bye.